So today's lesson is all about continuity. So we'll learn a little bit about continuity at a point, what constitutes a continuous function, different algebraic combinations and composites, and maybe a little about the intermediate value theorem for continuous functions. So all that will just kind of be done together, and it'll kind of separate itself as we go. Let's define what we mean by continuity. Any function y equals f of x whose graph can be sketched in one continuous motion without ever lifting the pencil is an example of a continuous function. So that's all continuity means, is that you can trace a graph from left to right and complete the graph without ever picking up your pencil. So let's talk about the definition of continuity at a point. A function is continuous at a point C if the following conditions are met. First off, the function has to be defined there. There has to be somewhere that it's defined. It can't be undefined there. Second, the limit there has to exist. That rules out all kinds of things. It rules out jumps, right? Asymptotes, yeah. So it rules out a lot of things already. And third, the limit as you approach the C value of that function has to equal the actual function value. The easiest way to say that is that a function is continuous at a point if the limit as x approaches that value C can be found by direct substitution. If you can't find the limit by direct substitution, the function cannot be continuous there for whatever reason. We say a function is continuous on an open interval as long as the function is continuous at every point in the interval. So most of the time, we talk about continuity on open intervals, but we talk about discontinuities at an individual point. And we'll talk about how to frame your answers for all of those things. So basically, there are three ways that continuity can be destroyed. The function may just not be defined at C, as in a hole or an asymptote. So you can see an example right here. If we let this be the C value, you can see that it's not continuous there because there's a hole there. Now the limit still exists there, but I couldn't find that by direct substitution because when I plugged in, I would get a 0 over 0. So a hole, even though it doesn't affect the limit, it does affect the continuity. It's still discontinuous there. The limit may not exist at C even though the function is defined there. So that's the second way that continuity can be destroyed. That would be like a breaking point of a piecewise function. That's sometimes called a jump discontinuity. So the function is defined here. There's the y value of the function, but the limit doesn't exist because the left limit and the right limit aren't equal. So holes disrupt continuity, jumps disrupt continuity, and third, the function may be defined at C and the limit may exist at C, but the two values may be different, which can also happen occasionally on a piecewise function. So over here, we can see that the limit exists from the left and the right, but it's approaching a hole, and the function value exists down here. The two just aren't equal. Vertical asymptotes also affect continuity, and we'll kind of look at that, but we already expected that because the limit doesn't exist as you approach a vertical asymptote, right? Because of the unbounded behavior. So anywhere a limit doesn't exist is automatically a discontinuity. So let's pause and see if you have any questions so far. A place where continuity is disrupted is called a discontinuity. Discontinuities can pretty much occur only at the edges of the domain where the denominator equals 0 or at the breaking points of a piecewise function. So those are the things you need to be on the lookout for. Edges of the domain where the denominator equals 0, and that could be a hole or a vertical asymptote, or at the breaking points of a piecewise function. That's where you're going to find your discontinuities. An oscillation would show up as a denominator equaling 0. There are two types of discontinuities: removable, usually a hole in the graph, and non-removable. That's usually an asymptote or a jump in the graph. An oscillation is also non-removable. The only removable discontinuity is a hole. And you can always see those because you can remove them algebraically by usually factoring in, canceling, or rationalizing some of those things that we did when we found algebraic limits. So here's an example of a removable discontinuity. There's a hole here. I could remove it by simply putting a dot there. A single dot would fix it. That's called removable. There are two types of non-removable: jumps, and we didn't have one of an asymptote, did we?
I don't think so.
Okay. Do you see how this one's also removable? Why is it removable? I could take this one point and move it to there and it would fix it. So just think of holes as removable, everything else is non-removable. Jumps, asymptotes, and oscillations. The only thing we're going to talk about that is removable is going to be a hole. Everything else we'll label as a non-removable discontinuity. Okay, so just for the sake of learning, I'm going to ask for these examples that we just fully discuss the continuity of the functions in question. Okay? So the first one we're going to discuss is f of x equals 1 over x. So we're going to discuss where it is continuous, and we're going to discuss where it is discontinuous. And the places where it is discontinuous, we'll decide whether those are removable or non-removable discontinuities. Okay, so let's look at 1 over x. This guy, the x value in question, can be anything at all except what? 0. X can't be 0. What's happening where the denominator equals 0? How do you know it's a vertical asymptote rather than a hole?
Because you can go on either
But how do you know just by looking at it? If I plug in 0 there and I get 1 over 0,
That's in the power rule.
that's a horizontal asymptote. How do we know that that's a vertical asymptote occurring at x equals 0 and not a hole? Okay. Guys, here's how you know. If you get a non-zero number over 0, that is always a vertical asymptote. A 0 over 0 is usually a hole. But a non-zero number over 0 is always a vertical asymptote. So we know that's a vertical asymptote at x equals 0. Everything else is fine. Every other number in the world is fine. There's no reason to be suspicious of any other number. That's going to be the only problem for what we call a rational function, is where its denominator equals 0. So we know that this guy is continuous everywhere except, so we say that it is continuous from negative infinity up to 0. And then there is a discontinuity at 0, so we put a parenthesis there. And it's continuous everywhere after 0. Those are its intervals of continuity. So we list everything from negative infinity to infinity, and we leave the 0 out. Then we talk about where it is discontinuous. So we're going to talk about its discontinuities. It only has one. What is it?
0.
At x equals 0. And is that discontinuity removable or non-removable if you were asked to classify? Because it's an asymptote. So you could mark it as NRD or RD if you were asked to. So we'll pause right there and let you digest that. Okay, for the second example, we want to fully discuss the continuity of the rational function g of x equals x squared minus 1 over x minus 1. With rational functions, functions that have variables in the denominator, all you have to worry about are where the denominator equals 0. So we know just by looking at this that the only place my continuity is going to be disrupted is at x equals what? 1. All we have to do is determine whether that discontinuity is removable or non-removable. And the way you do that is you look to see if the top will factor, and if it does, will it cancel with the denominator? That means that it is a whole, not an asymptote. Another way to do that would be just to plug 1 in. If you just substitute 1 in, direct substitution gives you 0 over 0. We know it's not an asymptote. And with rational functions, 0 over 0 is indicative of a whole. Now, in some functions, such as absolute value, it's indicative of a jump. So you have to be careful. But if you can factor and cancel, or rationalize and cancel, and what we call remove the whole through algebra so that you could then find the limit, then it's a removable discontinuity. It's still a discontinuity at x equals 1, but there's a whole there. So we say that this function is continuous on the interval from negative infinity up to what number?
1.
Positive 1, and it's an open interval there, it has a parenthesis, and it's also continuous from 1 to infinity as long as we don't include the 1. So that's where it is continuous. And so on different assessments, sometimes you'll be asked to tell where it is continuous, and sometimes you'll be asked to tell where it is not continuous. So you just have to read carefully. Let's talk now about where it is discontinuous, where its discontinuities are. There's only one at
X equals 1.
and we determined that it is removable. So be careful. Sometimes you're asked to specify whether it's removable versus non-removable. You can also look at a graph if you're not sure. If you can't see it when you look at your graph, then chances are it's removable.